So after that, now we need to consider another several important parameters as well. So the first one is the noise. Actually, when you design the sensor, one sensor, responsivity is almost the most important one we need to first to identify. Okay. However, without understanding noise, you cannot get the final result of the signal to noise ratio. Actually, how to define the signal is detectable. That totally depends on the signal to noise ratio. It not only depends on the responsivity. For example, some sensor you can define, do very good design for very high responsivity. However, at the same time, if you have a very strong noise at the background, you still cannot get a very good signal to noise ratio. Okay, that means the signal may not be easy to be detectable. So that's a problem. So not only when you consider the responsivity, that means we can have a very high amount of the signals, but also we need to consider the background noise. We try to reduce the noise. But before we try to reduce the noise, we need to understand the sources of the noise. Where did they come from? Okay. So basically, when we come back to our original design of the structure, maybe we can count at 7.1. You come back to the design block diagram, the flow. So starting from the beginning to the end, actually there are several positions we can introduce noise into the system. Okay, the first noise will be the mechanical noise. We will talk about that later. The mechanical noise is regarding you put the cantilever beam and also the proof mass inside the ambient environment. The ambient environment has a lot of interaction. For example, like the gas molecule in the atmosphere, we're hitting onto the plate all the time. And also that heating power depends on the temperature as well. So if you have a higher temperature, you got a higher heating power. So you got a more vibration. Okay, you don't have before you got a signal. Actually, you will see the vibration itself. If you have the cantilever beam inside ambient. So this is from the mechanical part. We call it mechanical noise. So it's corresponding to the acceleration from outside, the interference from outside. It's not from our signal part. Okay, so it's not from our real acceleration. The part you want to do the measurement is from other resources. Okay, so this is the first one. We call it mechanical noise. So the second noise you can introduce into the system is the resistivity. Resistors, the piezo resistors. Because I have a resistor over here, so the resistor actually have electrons flowing inside the resistors. So the electrons, when during their transport inside the resistor, they will also encounter another noise. So resistive noise, and also related to the junction noise. The white noise is coming from this position. So the resistive noise also proportional to the square of your temperature. That means you have increased the temperature, increased the noise as well. Because when you increase the temperature, the electron transport inside the resistor can encounter more vibration of your atoms and also the materials inside your structure, the resistor structure. So the resistance become higher. So it's a bit tougher for the electron to pass in through the resistor. So they will make the noise higher. Okay, so this is the second one. And the third one is coming from outside into your electronic amplifier, the electronic circuits. But we are not going to discuss this in this lecture because we finish our design into the voltage, into the Western bridge stage. So beyond that is out of the scope of this course. So for the rest of the electronic amplifier design, it will be better for you to come back to the electronics IC design. Those are circuit related courses. and they will tell you the detail about the design. But here I just give you some idea, a very rough idea. The electronic circuits also can introduce noise. So here I will just focus two noise. The first one is the Johnson noise. The second one is the mechanical noise. So we will also estimate the noise level in our design, the current accelerometer, what kind of level and what kind of type, and also what's the final effect of those noise when we combine them together. Okay. So after understand the three important noise sources, now we come back to 7-3, the noise part of our lecture. Okay, so now I will focus on the first one. The first one is called the Johnson noise. As you know, Johnson noise is if you have a resistor, there's always Johnson noise. So so we have 4 resistors actually, unfortunately, in our Wheatstone bridge design. So each resistor will contribute a lot of noise. And also so the Johnson noise is an interesting noise. Sometimes we call it a white noise. Why do we call it a white noise? The white noise means doesn't matter it's in a low frequency range or high frequency range. The noise level usually is the same, doesn't change. It's like our sunlight. When you have a sunlight shining onto the ground, when you see the spectrum, so the power density for different wavelengths, they are similar, no difference. So when they combine together, the light becomes a white light. Okay, so the noise has this kind of similar characters. That means no matter it's a low frequency or high frequency, you got this noise. The noise power will be the same. Okay, at a different kind of spectrum. So the noise power is contribute 4 kT per hertz. So we are talking about different frequencies from low frequency to high frequency. So when you operate the system in high frequency or low frequency, no matter what kind of wavelength or frequency, you always get this kind of noise. So when we consider the frequency response, so usually we will think of easy, simple figures. Let's at the window. So the frequency. So this is DC from 0 to omega n, omega 0. So if the system is not the under-damped system, it's critical damped system. So the curve will similar to the curve I'm currently drawing. Okay, beyond this point, the window is closed. So when no matter what kind of signal come in, there will be no response. Okay, but before that, the response will be equal to 1. Okay, the normalized response. Okay, will be normalized to the original response will be equal to 1. So that's the window you open for the system. For the white noise, it contributes noise power everywhere from 0 to infinity. There's a Johnson noise. There's a noise power for the Johnson noise. So this is your input. This is from your environment. Okay. So the Johnson noise encounter your system. That's your system. Your system open up a window to accept the noise get into the system. So the open up window, it depends on the frequency response. So if you have a very high frequency response, that means that you have a large window to accept the noise get into the system. Okay? So that's why sometimes we call we have a very high frequency response system. Usually the system will become very noisy because you have a lot of noise coming to the window. You open a large window because Johnson noise is a white noise. So no matter from low frequency to high frequency, the noise level, the power is the same. It's the same. So the final noise power will be the integration of this product and also the window open up. So you have a large open window. You accept more noise into the system. you got a final integrated noise will be higher, much higher. Okay, this is a typical problem. So if you want to design very high frequency response sensor, usually you will suffer also from the high noise because you open a large window. That's why when operation of high frequency for some very high sensitivity sensor, so in this case we will consider not to open up the window that wide. Okay, we'll consider using some kind of filter. Okay, to filter out our signal. So through a filter, for example, if your operation range is not in this range, maybe in some kind of omega 1, this range. So we open up a window, the filter, in only this range. So now the window will become smaller. Okay. So omega 1 maybe is very close to omega 0. You want to make this frequency response as high as possible because you want to measure some kind of high speed signals. Okay. So, but you want to focus on that part of signal. You don't want to detect other part of signal, including the noise. So you restrict the window by using filter. Okay, to restrict the window only in a narrow region. Okay. Okay. So so in this case, we can shorten the window size and get much less noise at the same time. So that's a way to reduce the noise. For example, like in the final project, if you choose a gyroscope, okay, we have 7 different topics, right? The first one is the gyroscope. Gyroscope, actually, the operation of gyroscope is also kind of the inertial sensor. For most accelerometer, they measure the linear type acceleration. Okay, for gyroscope, they are used to measure the angle variation, the rotation of the object. So the movement of the object can be divided into the linear translation and also the rotation. Okay, in 3-dimensional direction. So so the accelerometer is used to measure the linear acceleration, but the gyroscope is used to measure the rotation, how fast you rotate. Okay, so if you got information about the translation and the rotation of the object, you are totally understand how and why and the final destiny and also the trajectory, all those kind of things, the information about the object. Okay, for red gyro, usually they are operated in a natural frequency. Actually, the operation mode is they are vibrating all the time in a natural frequency. Okay, so if you don't do any filter, the gyroscope will be operated here, and if you don't have a filter, you need to open up the whole window for operating a gyroscope. So the gyroscope will become very, very noisy. So that's why when you're operating gyroscope, because we take the signal only in that natural frequency part, so maybe we can consider just fix our information. Okay, the input information, getting the information only in this small region, in order to reduce a lot of noise going to the signal channel into the system. Yeah, it's a little bit difficult to understand, but when you do the real design, you will get some idea, okay, about the situation. So the noise. So now we come back to the noise. So so the resistor encountered the white noise. So the white noise is the same power 4 kT everywhere, okay, from low frequency to high frequency. So no matter how you change the window of your frequency response, you never get rid of the Johnson noise. You always have Johnson noise. It's everywhere. Okay. So Johnson noise coming from, like I just mentioned, is from the thermal agitation of electrons within a resistor. So when the electron go into the resistor, you will feel the vibration of the environment. So the passing through will not be that easy. Okay. So it gives up the noise. And it's a 4 kT per hertz. Okay, it's a power. So we can write down the power equal to Vn means the junction noise equivalent voltage. Okay, V squared over R. Okay, that's a power. We can use like a IR or V squared over R. Okay, to represent the power. Okay. So finally, because of the power is equal to 4 kT, so we can put the 4 kT here. Okay, 4 kT means it's a fixed per hertz. However, the noise increase with the temperature increment. So increase the temperature, you also increase the noise power. Okay. So in out, you can find out the Vn, the noise equivalent voltage, will be this formula, 4 kT times R, and also this per bandwidth. So we can, the bandwidth means the window. Okay, how large the window we open up. So this depends on from DC to your natural frequency, how large the window, the frequency response you have. So we times the delta F. Delta F means the bandwidth. The bandwidth means the working range of from low frequency to high frequency. What's the working range? The window, the size of the window. So delta F means the hertz, how many hertz you have for the window. Okay. So now you got the final voltage equivalent, noise equivalent voltage equal to square of the 4 kT R times delta F. That means the noise will increase with the temperature, increase with your resistance. So you have a high resistance, you have high noise. That's why we sometimes ask you not to design your resistor too large. Okay? I usually in the homework give you the resistance around like kilo ohm maxima. Okay? From 100 ohm to kilo ohm. That's the reason, because you have if you design it into mega ohm, you will see a lot of noise. Okay, in your circuit, in your resistor. And also, sometimes we don't want to design the resistor too small as well. If you design it too small, actually you got a lot of current, and also the accuracy is not good enough. Because no matter what kind of fabrication process you are using, you also have some kind of fabrication limitation. So for shorter or for smaller resistor, you have a lot of non-accuracy. So that's a problem. So that's why we usually fix our resistance, design our resistance in a range between tens of ohm up to tens of kilo ohm, in this range. So it's very rare to design the resistance beyond like hundreds of kilo ohms or even mega ohms. It's very rare. Okay. Okay, so this equivalent noise equivalent power.